So what I did in undergraduate was join a team, a student organization. Ours was called Mudd Sub, but it's part of a larger competitive organization called RoboSub, um, which has colleges from everywhere compete in an underwater robotics competition. So colleges from the US, but also from Asia and Europe will compete in this organization, in this competition. And just to give you an idea of what this looks like. So here is a video. I can't go full screen. Hopefully you can see this okay. There's no sound to this, I don't think so. So you can see here that this robot was going through that orange gate. I don't know if you saw it. But down here, they give you a sense of what task the robot is currently doing. So currently it's looking for a red buoy, that one in the middle. And all of this is autonomous, so nobody is controlling this. So if you're interested in robotics in high school, you'll probably find this fairly interesting. And even if you're not, I feel like this is also interesting just because it's, I don't know, I find robots very interesting. Yeah, so we did the red buoy. Now he's searching for the green buoy. Right, and you can notice that the robot kind of does like a searchlight pattern, where it'll swivel to try and find the buoy that it's looking for. And I should be looking for the yellow buoy. Yep. So you can see it kind of, yeah, it's swiveling here a little bit. And I think the goal here was just to like run into each of the buoys was the goal of this particular task. So in these competitions, there's multiple tasks to accomplish. So at the beginning, they looked for the orange gate or the red gate or whatever it was. They should have tried to do the yellow gate right there. They should have tried to go through that, but unfortunately they didn't have time. So this was from 2017. And just like high school robotics, the competition, like the different tasks will change each year. So you can't just like bet on particular tasks being there and then just like develop for many years. You're always on your toes. Oh, next one. Is that? Yeah. Okay. So in terms of what makes this robot work, there's a lot. So if we go into just the very abstract categories, we can say, well, there's software and there's hardware. And hardware is everything that has to physically be built into the craft. So that's thrusters, cameras, hydrophones, maybe a claw or torpedoes. Those were on there when I was part of it, because there were a few years where the competition didn't happen because of COVID. And on the software side, you have things like navigation. How do you control the robot? Using computer vision to find out the different things around you. You can use hydrophones as well. This also comes into play. Mission control, which is trying to sort of like a state machine that tells you what particular task you want to be doing now. And SLAM, which I will talk about in a bit. And this plays into these computer vision and hydrophone teams as well. So these aren't just separate categories, they're kind of built on top of each other. So this is the model of our robot. His name is Alfie. He's a cute little boy. So he's got 4 vertical thrusters. You can see these ones down here, and then 4 horizontal thrusters as well. And these are diagonal so that we can easily do rotational motion. And if one of these fails, then we're not completely stuck in the water. And here he is in real life. He's a little bit less cute, but you know, he's always changing. This is him with his innards exposed. So this is all the electrical components that come into play. And here you can see a camera. And I think by the time that I left, we had 2 cameras, 1 at each viewport. But he's always changing, right? So this isn't just like you build it and you're done. You're always working on making it better, fixing things. But yeah, and on top of this, you would have this sealed hatch, and you could also look through. There was a viewport there as well. And this is a cameo from one of the professors of Harvey Mudd, his hands right here. So an interesting thing to note about underwater robotics is that, I just lost my screen for a second. Can everyone still see my presentation? I just like flipped off the screen. Okay, cool. Thank you. Yeah, so an interesting thing to note about underwater robotics is that it's a lot like aerial robotics. So if you've seen quadcopters like this, or maybe even like other designs like an octocopter, or just like aerial drones, the idea is very similar because air is also a fluid like water. They have different properties, but when it comes down to it, you can model vehicles traveling in this space very similarly. So when you're designing things like this, you can often look for research papers that are done on aerial vehicles like this, and then apply them fairly similarly to underwater vehicles. Okay, so this is the first thing that I'm going to be like talking about sort of deeply. So this is an interesting thing that I always like to talk about because I just find it super curious, and you may have actually seen it before. It's called SLAM, and it stands for Simultaneous Localization and Mapping. So by the name, what this means is that we simultaneously can move around in our environment, and while we're moving, we can also create an internal map of our environment. So we can do 2 things at once, which is, for us, very convenient. Here is a little video, although if I can't full screen, then it's going to be a little tough. So here's a robot that is using SLAM, and then this is the map that's getting created while it's moving. All right, and that's the path it's taken. And it's hard to see here. I can, okay. You can sort of see these sensors going out. They're like little tentacles that are kind of reaching all the edges of the environment. And then this is the actual map that's getting created. Slideshow. So the idea then, let me get back to that. Like this, you can sort of see that while we're moving, we're also sending out a bunch of sensors. So this can be lasers, this can be sonar, this can be computer vision. And there's a lot of ways that you can sense the environment around you, and then you build this internal map. So the great things about this are that you build a map of an unknown environment, and you can simultaneously localize the position and direction of the robot, and you don't require any GPS, which is awesome. Because in situations where you don't have like satellite coverage, or maybe you're like in a dense forest, right? We can't rely on having a connection to something above us necessarily. Or if you're indoors or maybe like really deep underground, things like that. Go forward. All right, yeah, so how does this actually work? Well, as I mentioned, you can use lasers or sonar or computer vision, computer vision being like the most computationally expensive of all these. So in the past, until more recently, we've been using lasers and sonar as more of the more common way of implementing this. And the things that are required then are a good estimation of our robot's state. So that includes position and like orientation of the robot. And as we go, we basically create a lot of probabilities based on what we're observing. So we send out a laser or sonar, and we get back some wave or some light wave or some sound wave, and based on the time that we can like track for that wave to hit us back, we can create some probabilities based on those waves, and then start to map our own environment around us, which I think is pretty cool. All right, and then the other thing that I wanted to talk about is reinforcement learning. So you may have touched on this in lecture a tiny bit, maybe the first or second day of lectures. A quick definition of reinforcement learning. Well, maybe not a definition, but the goal of reinforcement learning is that we want to make an agent, robot or Pac-Man, learn optimal actions based on some reward function. So the idea is that we'll begin by taking random actions in order to understand what gives us a reward and what doesn't give us a reward. So each action will be associated with some sort of reward, either like a 0 or a negative or some positive reward. And the idea is we want our agent, in this case, Pac-Man, to find the most rewarding path in the least amount of time to get to some end state. So we start at some start state, and then we end at some end state, and we want to end with the maximum reward that we can. And this reward can basically just be like a mathematical reward that we tell, hey, I want you to keep track of this reward, and I want you to maximize it. So as it starts to explore, it starts to understand, oh, this particular path, i.e., if Pac-Man's getting more dots, it sees, oh, if I get more dots, I get more reward, so I should keep trying to get dots. And then if we reward like grabbing the big dot, then we'd say, oh, grabbing the big dot gives me even more reward, so I'll go get small dots and then get a big dot. And then once it happens to get a big dot and hit a ghost, then we say, oh, you get a massive reward. So then it's like, oh, okay, well, I'll go for small dots, then I'll find a big dot, and then I'll seek out a ghost. This is an oversimplification of what's happening, but generally that's like the idea of reinforcement learning. So yeah, so like machine learning that we've seen, reinforcement learning tries to minimize the errors, but in this case, we kind of flip it on its head, and instead of minimizing errors, we kind of say maximizing rewards. And one interesting thing to note is that even if we find like an optimal path, we don't stop exploration into other parts of the world, right? Because there might be a better a better a better option out there. And if we just stay on the reward path that we have defined, we might not find it. So we'll occasionally, and we define this by like a very low probability, we will occasionally take a random step in a different direction in order to just kind of explore the environment around us, just in case we're missing something. And in terms of the problem of robotics, a few things that we could use this for. We might want to find the optimal way through a course, right? So just like Pac-Man, not understanding the course, we don't really have any like ahead of time knowledge of what the course is. So maybe maybe we might want to find the optimal way to get through one of these courses. Although if they're changing all the time, that might be a little bit difficult. And you don't get like a lot of time to like train on these courses. So that might be a little bit limited in our specific use case, but in other robotics situations, contexts, that might be a useful application of this. And the other thing that we could do is we could also try to learn about our own dynamics of our physical system. So if we have this big matrix of the different parameters of our robot, but we don't know exactly what those parameters should be, then what we can do is we can say, okay, well, instead of taking steps like in Pac-Man, we can take steps in terms of like changing particular parameters, like adding to them or subtracting them. And then in a kind of confined, controlled environment, we can test on either a simulation or on the physical system to say, all right, I want you to, with this new set of parameters, I want you to take a step, and I will give you some expected new state of what I expect you to be at versus what you actually are at. And the closer you are to that expected state, the better reward you will get. And in this way, we can kind of reward the system for trying to get better to match what we expect out of that system. So finally, I just have a few takeaways. I know this was kind of high level. So I always like to remind myself that AI can often be used in ways that aren't obvious. So you will all go into very different things. You won't all be working on just like very similar problems or problem spaces. And it might not seem obvious that you can use AI in like things like art or history or some other like humanities field, but that doesn't necessarily mean that AI can't be used in those situations. Just like in this, where we say, oh, finding the dynamics of our system, that's like a very, like, we always do that by hand or with a lot of trial and error. So it might not be obvious that AI can do that because there might not be like a great situation for that. But this is just to show that, you know, if you try it, it might work. And it won't always work, but you can say you tried it and you learn a lot by doing it. And AI is a massive field with a vast quantity of applications. So whatever you want to do, you can try and apply AI in that case. And for me, that's robots. Robots are an excellent use case